So, and our next speaker will be Matthias Komelschek from the University Josef Stefan Institute and University of Ljubljana. And he will be speaking about anisotropic, Skyrmion, and Meron spin dynamics in centrosymmetric gadolinium palladium silica.
Good. Is this on? Can you hear me? Okay, good. Yeah, thank you for the introduction, and thanks to the organizers for allowing me to present our work here. So I'll be talking about spin dynamics of skyrmions and extra textures that we found actually in this material. But before we get to that, let's recap what a skyrmion is. I'm sure everybody already knows, but it's a localized whirl in magnetization. It's topologically stable, so there are topological numbers that you can assign to this. So the skyrmion number that protects this against trivial unwinding, which makes it stable against perturbations. But you may or may not know, there's also a similar texture, basically a Meron. It's a half skyrmion. If you take the central part of a skyrmion, basically that's already a Meron. The outer part, if you could separate it, it would be an anti-Meron. So you could say a skyrmion is like if anti-Meron ate a Meron, basically, together. This will become relevant later. So skyrmions, they're easy to manipulate. So they've been proposed for data storage in racetrack memories, as we heard, spintronics as well. So you can do logic gates with skyrmions by driving skyrmions around. So they tend to repel as well. So you can do logic, reservoir computing, so for AI applications, and many other applications. The issues are, if you use bulk materials, at least their stability in the phase diagram, typically they're found in a small pocket somewhere in many materials, and they're quite large often. So the ones I'm talking about that have this problem are those that are the most common. So those that don't have any inversion symmetry in the crystal lattice, which allows for bulk Dzyaloshinskii-Moriya, so bulk chirality, that imprints into the chirality of the skyrmion. So the skyrmion has spins that are rotating, and this is helped by the crystal being chiral itself. If it has a preferred direction of rotation, plus entropic effects, usually stabilized skyrmions, but they're quite large and sensitive to external conditions. But we have many examples. So primarily B20 materials historically, and then thin films as well, which solve many of these problems in another way. But recently, so a few years ago, centrosymmetric skyrmions were also discovered. So in materials that have no preferred chirality, no preferred twist to the crystal structure, still we find chiral magnetic textures for some reason. People don't know what is the origin of that. So there's no bulk Dzyaloshinskii-Moriya that would extend across the whole crystal. So there are other proposals, frustration being the dominant among them, so competition between different types of interactions. So RKKY interactions are long-range, dipolar ones are as well. If they compete somehow, maybe that prevents trivial textures from stabilizing, and you'll get a complicated texture like a skyrmion in a material. Experimentally, though, they're extremely robust in the phase diagram, and they're much smaller, so only a few nanometers, which makes them potentially much more useful for applications as well, if you want to have dense data storage. But because we don't understand the mechanism that's stabilizing them, it's very hard to find new materials that would realize them. There are only a handful that are known till now. And people are working a lot on elucidating the mechanism. So there are theoretical proposals that compete, and we don't know what is the actual reason for stability. So this is where we came in. So we were studying the first centrosymmetric skyrmion material that was found, gadolinium palladium silicide. It has an inversion symmetric triangular lattice. We synthesized single crystal samples of this with our colleagues in Warwick University. And then, this is the phase diagram that one gets for this. So the high field phase is understood. This is a single Q fan phase, kind of trivial. There's a skyrmion lattice phase that has a non-known stabilization mechanism, as I discussed before. And the ground state is also actually unknown. Experimentally, we know it's a scattering with at least 3 Q vectors, but we don't know whether these are 3 different single Q domains, like the higher field phase, or is it a single domain that has a superposition of different modulations, making it multi-Q, like the skyrmion phase. What we found as a preview. So in the skyrmion phase, at least one part of the stabilization is due to anisotropy. So bulk anisotropy is still important, even in this centrosymmetric material. And the ground state is actually multi-Q. It's a Meron anti-Meron lattice, actually. And it's highly anisotropic as well. So how did we get to this? So we used muon spectroscopy. If you don't know about this, so you go to a large accelerator, you have a proton beam that impacts onto a graphite plate. This produces a beam of muons, all with the same polarization of the spin. And if you put this beam onto a sample, because the muons are charged, they very quickly stop inside a sample in less than a nanosecond, and then their spin starts to slowly precess around the local field. And you can track this precession by looking at the decay products of the muon. So the muon inevitably decays after a few microseconds, and you can see in which direction the positron that is emitted gets emitted. So you can put detectors around and track how the precession of the muon spin went in your crystal. If you see a signal like this for the difference between forward and backward positrons, you would say that you have a static homogeneous field across all the positions in the crystal where the muon could stop. And from the frequency, you could read out the strength of the field in principle, if you knew where the muon stops. So in our case, we found this kind of signal where you have the short time behavior that decays very quickly. It's not a nice cosine. This means you have a broad distribution of internal fields, which is of course expected. For any incommensurate magnetic texture, the spin can stop at any point along the incommensurate modulation, so you get a broad distribution. But at late times, we also saw some relaxation of the muon spin, which is due to dynamics. So we could track how the magnetic fields in this texture are fluctuating spontaneously. Now, how to interpret this signal at late times? Well, there's a connection to the fluctuations of the magnetic fields in the direction perpendicular to the detector direction. So in our case, we had two different pairs of detectors, one along the out-of-plane direction, one in plane. And it's the components of the fluctuating fields that are perpendicular to the detector direction that relax the muon spin in experiment. You don't need to remember all of the details, but the upshot is, so if the crystal is uniaxial like ours is, we expect basically isotropic fluctuations in plane. Then from two sets of measurements, so two detector combinations, you can extract separately the in-plane and the out-of-plane fluctuations. So you can see how much the fluctuating fields fluctuate in plane, what is the component there, and what is the component of the fluctuations out of plane. So to interpret our experimental data now, so the short time behavior is kind of trivial. So we see just the onset of magnetic order at the temperature where you would expect this IC1 phase to appear, the low temperature, the low field phase. But the dynamics have different relaxation rates for the two directions, out of plane and in plane. And if you transform this into the components, you see that the in-plane magnetic component is dominant. So the fields predominantly fluctuate in plane, linearly in temperature, but the out-of-plane fluctuation is basically suppressed completely, which means that it's either not present or at much higher frequencies than what the muon can see. In any case, so this anisotropic temperature dependence, where qualitatively you have one is linear, the other is constant in temperature, means that this is not a single Q phase. So at least simple single Q phases, like spin spirals or helices, you have a nice prediction from spin density wave theory that both fluctuation rates should be proportional one to the other. The idea there is basically you have just one bosonic degree of freedom at the bottom of the Magnum band, which is the only thing that the muon is sensing. It's sensing very low frequency excitations, nothing higher. And this one dominant point contributes the same up to a prefactor to both relaxation rates, to both correlation times, meaning that we should see something isotropic, but we don't. Okay, so this excludes simple scenarios like the single Q spiral that was proposed as the ground state of this material potentially in favor of a multi-Q state. So multiple Magnum bands at low energies. If we combine this with previous measurements that were done in this material, resonant X-rays and topological Hall effect. So resonant X-rays saw either 3 single Q domains or 1 multi-Q phase. We see multi-Q. They also saw topological Hall effect in this regime of low fields. And the conclusion was basically from the paper, if they could exclude the single Q domain scenario, the only thing that would be left is the Meron anti-Meron lattice as the ground state. And this is exactly what they found. Basically, it's a multi-Q state. So this kind of Meron anti-Meron lattice, which you can imagine also as the Skyrmion lattice splitting in halves into Meron and anti-Meron pairs. Okay, this is the first part. We also looked at the Skyrmion lattice phase. We also saw anisotropic dynamics. Here, the out of plane fluctuations were dominant, which is consistent with the dominant excitations being maybe of this kind of type, clockwise rotations or anti-clockwise, whereas the high field phase was isotropic in dynamics and coplanar in the magnetic fields, which is all consistent with the prediction for the fan phase, so the single Q modulation that people have been satisfied is the explanation of this phase. Also, the power here in temperature matches precisely what you would expect for a one-dimensional structure with a Dirac-like dispersion around the bottom of the magnum band, so incommensurate structures. Okay, maybe just briefly if I flash the results of polarized resonant X-rays. So we also could separate separately the scattering due to magnetic and charge channels, and we could see what are the single Q components that make up these multi-Q phases that superimpose. And the high field phase was trivial. It's just a transverse density wave of spin, whereas the lower field phases were elliptical helices of Bloch type. And they formed separate domains of left and right-handed chiral helices, which is kind of strange. And the correlation lengths were long within the plane, but short between the planes. In the end, this means that, so our interpretation is, you have layers of gadolinium. So even though this is a 3D metal, it seems that the layers don't talk much amongst themselves. This could be a frustration effect where the one layer wants to induce something in the other layer, but there are so many interactions that compete that it cannot really force the other layer to do anything very specific. So you get separate domains of clockwise and anti-clockwise skyrmions in your material, vertically stacked, one on top of the other. What could cause this? So within a single layer, the space for layers that are non-magnetic between the gadoliniums are locally chiral. So one layer has a preferred chirality actually, but this chirality just switches between the layers. Okay, and this allows actually for local Dzyaloshinskii-Moriya interactions, which we simulated with macromagnetics to find that indeed it prefers one chirality over the other. It prefers a Bloch type modulation, as we see in experiment. We could estimate the size of the Dzyaloshinskii-Moriya interactions and the directions just from symmetry arguments. And due to the global inversion symmetry, we reproduce the experimental ratio that there are as many left as right-handed domains stacked vertically on top of each other. And with that, that's the summary. So we found anisotropic spin dynamics with a Meron anti-Meron topological ground state. We saw quasi two-dimensional locally chiral magnetism due to local Dzyaloshinskii-Moriya interactions, even though this is a centrosymmetric material where we would expect that this wouldn't be an important effect if the layers were talking strongly one to the other. And I'd like to acknowledge my collaborators, the group I'm working at, the Joschel Stephan Institute, and just to flash, at our institute, we also have a large opening so for postdocs, 40 positions co-funded by Marie Curie in all kinds of areas in quantum magnetism or in quantum technology in general. Okay, with that, I'd like to thank you for your attention and ask any questions.
Thank you, Mateusz, for your talk. We will have a question here.
So thank you very much for the extremely interesting talk. So right at the end, you give us sort of your interpretation of the origin of this phenomenon, attributing it to local DMI plus RKKY. But I didn't understand. Is that just a sort of speculation, or did you do, for instance, DFT calculations? Is it based on?
Yeah. So this is in the category of speculation, basically. So it's not being calculated by DFT. We're trying to do that now, actually. So that's the plan, to calculate this from first principles. But in principle, DMI is supposed to always be the first perturbation that you have to any kind of isotropic thing, as long as it's allowed, as long as there's some local chirality. But previously, people neglected this effect because globally, the whole unit cell is achiral. But actually, it matters what is within one layer because the layers don't talk enough. So locally, actually, there are DMI interactions that are allowed, so expected to be strong because of that.
Thank you.
Thank you.
Are there further questions? If not, I think we can thank Mateusz again.
Okay.